Okay, let's take a look at chapter 16, different models that we have here to determine probability of different events. And let's start with the very, very famous Bernoulli family. It's an extended family. It was a lot of cousins, really at the forefront of a lot of development of several different forms, different branches of algebra, and very much on the forefront of trying to describe probability of games of chance. Um, so um, these trials that they're referring to here, um, based on the work of Daniel Bernoulli, we call something a Bernoulli trial if whatever it is that we're describing, there are just two possible outcomes, usually defined as success and failure. The probability of success is a constant that we know, and one trial to the next is independent of all the ones that came before it. So, one of the most important things here is, again, um, in your book, it talks about, I really don't want to get into it too much, um, a serial manufacturer putting in trading cards of famous people, and you want to get a complete set. Well, you buy a box of cereal, see whose card is in there. You buy another box of cereal. Yeah, the second box, whatever card is in there, is independent of whatever was in the first box. Um, and this is often an underlying assumption here when they're doing political surveys. Again, you keep coming back to that time and time again. There are not an infinite number of American voters. So when you sample, when you talk to one particular voter, um, you don't put that person back into the population and have the possibility, albeit remote, that you contact that same person again. Okay. So the trials, if we're doing a political survey, the trials technically are not independent. But if we have hundreds of millions of eligible voters and we do a survey of, say, 1,000 of them, this is where we get to what they call the 10% condition. Um, it's okay to proceed as long as the sample is less than 10% of the population. Now, you couldn't do this, say, let's on the other side of it there, a deck of cards. When you're dealing out cards, playing Go Fish or whatever your preferred game is, you're doing, again, sampling without replacement. Those are not independent. I mean, what if you have any twos, depends upon the cards that were dealt out. But again, 52 cards in a deck compared to hundreds of thousands of eligible voters, those are very, very different. Okay. So the 10% condition, we can go ahead, even if the trials are not independent, as long as the sample is less than 10% of the population. All right, so let's look at a few examples here. Are these random variables based on Bernoulli trials? If so, why? If not, why not? The wait staff at a small restaurant consists of 5 men, 8 women. They write their names on a slip of paper. Boss chooses 4 people at random to work overtime on a holiday weekend. See, now this was back when restaurants were still open. We count the number of females who were chosen. So my response is no, that is not a Bernoulli trial. The population is so small. Every time that you pull a name out of a hat, the probability of choosing a female changes every single time. So, no, well, first of all, they're not independent, and we're taking something that's way more than 10%. Part B, in the US, about 1 out of every 90 pregnant women gives birth to twins. Among a group of pregnant women who work in the same office, we count the number of them who gave birth to twins. Yes, I would say that we could say that is a Bernoulli trial. We don't know how big the office is. Among the group of pregnant women who work in the same office, we count the number of them who give birth to twins. If we're talking about, some big insurance company, in a building that's got 13 floors or whatever. Part C, we count the number of times a woman who's been pregnant 3 times gives birth to twins. No, I don't think that works. Women who've had twins are more likely to have them again, so that violates the idea of being independent. We pick 40 M&Ms at random from a large bag, counting how many of each color we get. This does not qualify as a Bernoulli trial because there are more than just 2 outcomes. Okay, you should remember that. Hello. There would have to be just 2 possible outcomes. And in this case, there's a lot more than 2 colors. Part E, Small Towns Merchants Association says that 26% of all businesses are owned by women. You call 15 businesses randomly chosen from the 77 listed from the website for the Merchants Association, counting the number owned by women. Okay, so there's only 2 outcomes. Is it owned by a woman or not? That's fine, but hold on. If there are 77 listed on the website, 10% of that would be 7.7. You've called more than you've violated the 10% rule. Okay, hopefully that makes sense. Now, there's not going to be anything specifically on the AP exam asking about Bernoulli trials, but this is the basis going forward of these 2 major models that we're going to talk about here in Chapter 16. The first is the geometric model. Okay, so if you'll take a short little walk down analogy lane here. On an Algebra 1 test, you're not going to be asked a question about variables. You're going to be given an equation and asked to solve for the variable. Okay, it's the same kind of thing here with these 2 models. They're all based on Bernoulli trials, but they're not going to ask you anything specifically about a Bernoulli trial. All right, so here's a big concept here. We're going to call this a geometric probability model. If we're looking at a random variable and we're trying to count the number of Bernoulli trials until the first success. Okay, there's one parameter, P, the probability of success, and then, okay, the notation there, geom parentheses P. So for our variables here, well, there's a few things you need to know and then some formulas, okay? So P is going to stand for the probability of success, however we define that. Q then is going to be the complementary probability. In other words, the probability of failure. Remember, for a Bernoulli trial, there can only be 2 outcomes, okay? So X is our random variable there of the number of trials until the first success happens. Okay, so that probability is going to be the probability of failure raised to the x minus 1 power times the probability of success. Okay, now those ones down at the bottom, make sure you catch these. Okay, E of x, that's our expected value. Okay, we used that in the last chapter, I believe. The expected value is, of course, mu, the mean. That's simply going to be 1 over the inverse of the probability of success. Okay? And then the standard deviation for this is going to be, again, you're going to have to get used to this, the square root of q divided by p squared. Now, again, it's my understanding that those two formulas down at the bottom will be part of the table of values on the AP exam. Okay, so to find mu, to find the mean, it's just 1 over the probability. And for sigma, the standard deviation, square root of q divided by p squared. Okay, so now that's a geometric model, the number of trials until the first success. Now we got to compare that to a binomial model. That'll tell us here, for a fixed number of Bernoulli trials, how many successes are we going to get out of that fixed number? Okay. We're going to need 2 parameters for a binomial. We're going to know how many trials we're going to run, and of course the probability of success. Okay. Now again, I'll hopefully show you how to use the calculator. Your N spires, hopefully you brought those home too. We'll go through that. All right, but formulas you need to know here. Wow, that looks familiar. You have to, if you'll pardon the pun here, you have to find the right combination of numbers. Yay! So again, n factorial divided by k factorial times n minus k factorial. N choose k. And again, your calculator will do that for you. So the binomial probability here, n's going to be, again, how many trials we're going to run. P is the probability of success. So again, Q is going to be 1 minus P, the probability of failure. X in this case is going to be, our random variable here is the number of successes in n number of trials. Okay. So to find our probability here, you're going to multiply 3 things. Okay. So you're first of all going to find that combination of n choose x. We're going to multiply that by the probability of success raised to the x power, then multiply by the probability of failure to the, basically the complementary of n minus x. The mean is really simple here. All we've got to do is take the number of trials and multiply it by p, the probability of success. That's going to be our value for mu. And our standard deviation, well, this is interesting. It's the square root of the product of 3 values. We're going to take n times p times q. All right, so let's try another just checking part of it here. Pew Research Center reports that it's able to contact only 67% of randomly selected households for telephone surveys. Suppose a pollster has a list of 12 calls to make. Why can these phone calls be considered Bernoulli trials? Well, to me, the implication is they're calling American adults. And out of all the people living in this country, is the 12 less than 10% of the population? Yeah, that's not, that's a pretty easy call to make on that one. And the other aspect of it there's only 2 outcomes. Either we called the number and we got a hold of them, or we called and we didn't. Okay. So then for part B, so we are going to use our lovely binomial model on this one. Find the probability that the 4th call is the first one that makes contact. Okay, so our value for P was given to us as 0.76. Our value for Q is obviously 0.24. So we're looking really, how do you want to shorten this here? First call, second call, third call, fourth call. And we're saying the first one is a failure, didn't get anybody. Second one's a failure. Third one's a failure. Fourth one, success. So what we're going to do is multiply those together. Obviously, when you type that into your calculator, you'll use an exponent there. And hopefully we'll come up with 0.011. Okay, so that's for part A. Part B, find the expected number of successful calls out of the 12. Okay, so again, going back to our little formula there, our expected value is mu, and that's simply n times p. Well, we're making 12 calls. Probability of success is 0.76, so that'll be 9.12. Part C, find the expected, I'm sorry, that was C. D, find the standard deviation of the number of successful calls. I apologize. That's B. This is C. Now D, for our standard deviation, we're going to take the square root of n. All right, so we said that there were 12 calls times P, success is 0.76, times Q, failure is 0.24. Again, we're going to multiply all those together and take the square root. So that should give us a standard deviation there of 1.48. Again, I think those are calls would be the unit of measure. Part E, find the probability that exactly 9 out of the 12 calls are successful. Okay, so again, this is just a straightforward binomial. So we're looking at out of 12, choose 9, and we want successes on 9 of them. And we are looking for the probability of failure on the other 3. Okay. So to refresh your memory there about combinations, with our lovely calculators here, menu, option 5 for probability. Oh, look, make sure that you choose the right combination. It's 3. So in this case, it's 12, comma, 9, and that's 220. And then multiply that by the 0.76 raised to the 9th, the right arrow to get to your next part of it here, 0.24 raised to the 3rd, and we'll round that off to something reasonable like 0.26. So that's interesting. Just a little bit more than 1/4 of the time, we can expect 9 out of the 12 calls to actually connect to somebody. Okay. Now for part F, notice how the verbiage changes so subtly, yet so importantly. Find the probability that at least 9 of the calls are successful. at least 9 includes the 9 that we just found, but I'm going to try and write this out and be consistent here. Out of the 12, choose not, sorry, not supposed to be a fraction. 12, choose 9 of 0.76 to the ninth times 0.24 to the third. Or out of those 12, 10 of them could be successful. So 0.76 to the 10th times the 0.24 now down to the second. Out of the 12, 11 could be successful. So 0.76 to the 11th times 0.24 to the first plus, did it again, 12, choose 12 of 0.76 to the 12th power, and of course that's times 0.24 to the 0. Anything to the 0 power is 1. Don't even have to write that down. My, doesn't that just look like so much fun to type that in? And that's only got 4 terms. Technology to the rescue. All right, I imagine you'll have to rewind and replay this frequently here. So menu, 5 for probability again. We're going to go down to number 5, distributions. Now, normally when we've been dealing with finding a simple probability of a normal function, or you know the probability and you're trying to work backwards to find the z-score, we're either sticking with 2 or 3. Oh, look at that. There's binomial. I'm sorry. We want our binomial cumulative distribution function. Okay, so that's option B. Ooh, look at this lovely window that pops up. All right, what are we describing here? We said that there were 12 calls, so that's the number of trials is 12. Let me run through that again because sometimes it goes off on its own. 5, 5, and then arrow down to choice B. So the number of trials is 12, tab. Probability of success, again, we said that was 0.76. We want to know the probability here that somewhere between at least 9, so 9's the lower bound. At least 9 of them means somewhere between and including 9, 10, 11, and 12. So 9's the lower bound, 12's the upper. And look at that. In less than a heartbeat, and again, we'll round that off to say about 0.68. Now, for the more skeptical out there, you can do all of that previous method there. But again, I would review and make sure that you know how to do that on the calculator. Man, that's so much faster. Okay, so let's continue here. All right, so there, yeah, part of it is direct calculations. All right, we saw that a little bit with that last one, and that was only 4. All right, had they asked, what's the probability that at least 3 of them are successful? Oh goodness. Okay, it's going to become tedious really, really quickly. As long as we're, again, just dealing with those 2 outcomes, success or failure, the binomial model is approximately normal. Again, never, ever, ever say that it is normal. Always put that disclaimer in there. It's approximately normal. If, again, here's a huge part of this. If this shows up on the AP test, this is going to be one of the points of credit that you're going to get. If we expect at least 10 successes and at least 10 failures, okay? So you're going to have to write this out and show that this success failure condition is met before you can do anything else. Okay, you have to be explicit in writing this stuff out. Okay, so say we just go back quickly to the previous one there. Again, we were talking about 12 trials and a success rate of 0.76. Oh wait, that's not good enough. Okay, so you got to be careful here about which ones you're using this on. Okay, we can use a normal model to approximate the binomial model if they're continuous random variables. Um, if we're approximating something that's discrete, use the normal model. We no longer calculate the probability that the random variable equals a particular value, but here's the fun stuff. It's in a certain range. It lies between two values. Okay, so let's look at the difference here. Um, they tell us that they are successful in contacting 76% of households randomly selected. When surveying public opinion polls, it's not 12. That one guy, one of their researchers, had a quota of 12 calls that he had to make. For the whole survey here, we're hoping to poll at least 1,000. Okay. Suppose they've compiled a list of 1,300 phone numbers to call. What's the probability that they'll reach enough people for the survey to be valid? Okay, so again, steps that we need to get to before we can get to that, to answering the basic question there. Despite the fact that pollsters sample people without replacement, can we think of these calls as independent trials? How many households are there in the United States? They've got a list of 1,300 phone numbers. Is the 1,300 less than 10% of all households? Yeah, again, when we have millions of people, hundreds of millions of people in the country, and it's only 1,300. Yeah, I think that's a safe conclusion there, that that's less than 10%. Find the mean and standard deviation of if X is the number of adults they may successfully contact. Okay, so again, our value here for mu is going to be the 1,300 times our probability of success is the 0.76. So that'll give us 988. They also wanted standard deviation, so we're going to take the square root, again, the product of n times p times q. Well, n in this case is the 1,300 phone numbers. Success is 0.76. Failure is 0.24. We'll round that off to something reasonable like 15.4. For part C, we want to find the probability that x is greater than or equal to 1,000. Can we use a normal model to approximate this binomial probability? Well, yeah, we just figured out 1,300 times the 0.76. That's greater than 10. 1,300 times the other q. This is 312. Both of them are greater than 10, so yes, it should hold. So then for part D, do the actual calculations then. Find the approximate probability that Pew is able to contact at least 1,000 voters on the list. So now again, we're asked to use our normal model. So back to what we did before, to find the probability of at least 1,000, we need to find out what the z-score is. So we'll take the 1,000, our target, subtract up here, we figured out what mu was, 988, divided by our standard deviation of 15.4. So that works out to be about 0.7792 if I go out to 4 decimal places. And then, so the probability that our z-score is 0.7792. Calculator time. Oops, calculator. So again, probability distributions 5, 5, and we're using our normal cumulative distribution function number 2. So again, at least 1,000, okay? So that z-score that we just found there of 0.7792, that's actually the lower bound. So we'll put that in 0.7792. At least means greater than, so the upper bound is something really big, like 10 or 100 or whatever it is you want. And again, quicker than you can blink, there's our probability, 0.2179. Okay. So this is going back to what we've discussed several times before. With our normal model, we need a z-score and then our normal distribution function to find the probability. We'll get into some more formal definitions here about what it means for something to be statistically significant. All right, for that last one there, we had about a 22% chance of the 1,300 phone calls would give us at least 1,000. So yeah, that shouldn't be all that surprising. Um, for now, it's enough to recognize that when a normal model is used, anything, I'm not sure where that 9 came from. I think that's a typo. Outcomes more than 2 standard deviations from the expected value are considered surprising. Okay, it's got to be more than 2 standard deviations off. Okay. Um, and again, we'll get into that later. But just the idea here that, well, the probability of out of those 1,300, at least 1,000 of them working and being able to contact somebody, the probability of that happening was 0.22. Okay, that's not great, but it's not impossible, and it's not even rarely going to work. Okay, usually our a cutoff point that's used frequently is say 0.05, and if we came up with 0.22, that's not statistically significant. Okay. All right, so just kind of wrapping it up, reviewing a few things. Bernoulli trials, you have to have two outcomes, and you have to have independence. and that 10%. Okay. Now again, the geometric and the binomial models measure very, very different things. Don't use the normal approximation if n is really, really small. Okay. Sorry. So we could be dealing with the geometric model. How many of these Bernoulli trials do we have to run until we get success? The binomial is out of however many trials, how many times are we going to get success? And then the normal model is basically if we can convert that binomial model into an easier way of calculating things. Okay. But again, to use the normal model, let me re-emphasize that one last time. We have to have at least 10 successes and 10 failures. Okay, so we didn't use that normal model on the second part of it here, where there were only 12 outcomes. You can't have 10 successes and 10 failures if you're only running the thing 12 times. Okay, yes, there are certain conditions that have to be checked, and you've got to write that out to demonstrate your understanding of it. Anything more than 2 standard deviations from the expected value is unusual. Name the distribution. Make sure that you're writing out the correct parameters, and for these, you need to have the right calculation. Okay. The name, you can say, it's binomial, it's geometric, it's normal. Have the proper formula. Um, use standard notation for parameters. Don't make up your own stuff. All right. Hopefully that gets you started. As usual, do your best to answer those questions. And as you go through that, give your best shot and then send me an email letting me know which ones you've got questions on. On OneNote, there should be a page in this tab that has the correct answers for you and short explanations. But I'll make another movie um, interpreting what they have written.